and record. So section 2.4 is going to discuss scatter plots. And scatter plots are what you can do with pairs of numeric data. So things of the form X and Y that you can graph on a plane. So examples of that, you might look at height versus weight. You could look at years of education versus IQ. You could look at your chance of a heart attack versus how much you smoke. All kinds of different things that are pairs of numeric data. And let's look at one set of data that's kind of close to us here in Michigan. Hopefully you got the links that I sent you earlier. This one's the coronavirus in Michigan. This is the number of new cases logged each day starting March 10th. So around March 10th, we had like 0 and then 2 cases, I think. It was probably the very first day, March 10th. So let's take a look at that data by clicking the circle to the left here. And you see 2 sets of plots here. The green dots are the actual data, and the purple dots are the 7-day moving average. We'll take a more close look at that in section 3.1. But for now, what you're seeing almost looks like a straight moonshot, and the number of cases just exploded until we got to sometime in early April. We had a maximum of almost 2,000 new cases in one day. Now, after that, we started getting a little bit of a control on things. So if you click the next circle, see how things kind of settled down a little bit. And through social distancing and proper use of masks and other things like that, we brought those cases down to below 500, but it's tough to keep that up forever. And as you unveil the rest of the data, you can see that, well, we did hit a minimum around mid-June, and then we've drifted back up, but it's nowhere near, thankfully, some of these highs in mid-May or mid-April that we saw earlier. So it's kind of nice because we're seeing a good picture of the progress of the virus through Michigan. Now the 7-day moving average is a little bit less scattered than the green dots, which are the daily reports of how many new cases we got. But in particular, let me look back at just the first part of this to try and head this in the direction that we're worried about. The first part of this looks like a straight line, pretty much, just a moonshot, the way it exploded with number of new cases increasing and increasing. And in this course, what we're going to try and be able to do is give an equation that represents the data there. Let's fit a line to that. And in that same kind of spirit, let me remind you of a few things about the equations of lines. First of all, the equation of a line is going to look like this: y equals mx plus b. And let's remind ourselves of a few things here. What's the m represent?
Slope.
Yeah, m represents slope. And b represents what? Y-intercept. That is where the graph crosses the y-axis. So those two things. Now, in particular, the slope is something that I want you to have a good handle on. So let me remind you some more about some slope. And this is about as mathematical as this course is going to get. This is the only time I'm really going to be talking about something that's really hardcore math. It's not, I'm going to be testing you much on this, but there are a few ideas that I'd like you to know. So for instance, slope is a ratio. It's the rise over the run. And let me show it to you with this little triangle diagram here. Slope is the rise over the run. The rise is the vertical change going from, say, this point to this point. How much vertical change is there? The run is the horizontal change. So the ratio of those two is your slope. Now, the bigger that ratio, the steeper your slope. So let's acquaint ourselves with some of that and some special cases of the slope. And for that, I'd like to go to another little Desmos link that I sent you. Should look like this when you open it up. So linear equations is the title. I'll put this in the chat real quick in case you've missed it someplace. So, more time for the chat. My chat's not opening up. Not sure. Hopefully you got it earlier. And what we're going to do is we're going to look at, first of all, some data, but more importantly, some different slopes. So right now you've got a line that as you move from left to right, this red line is sloping downwards. Now, if you want to enhance your settings here, if you hit the tool icon and click projector mode, it's just going to make things a little bit darker, a little bit more enhanced, maybe a little bit easier to read. Certainly it's not going to affect anything else other than that. But what you can do is interact with this website. And we can play around with the slope and look at different slopes. And what I'd like you to do is try and play around with the slope to the point that you can get your line through the data. Now you might have to move both of these things, the slope and the intercept. So here's your y-intercept. Let's move it down to 10, for instance. So 10, that's where this graph is crossing the y-axis. That's why it's called the y-intercept. It's because that's where it intersects the vertical axis. Now, once you made that choice or in concert with that, see if you can't figure out a way to get our line to go pretty much exactly through the data. Now, there's going to be more than one answer, but there's certainly some that are better than the others. So play around with that and see what you can come up with. See if you can come up with a good fit to that data. Because that's what we're going to be doing a lot in statistics, is trying to summarize, some data with an equation. It doesn't have to be just a linear equation, but linear equations are what we're going to work with.
I have a question.
Yeah, please.
I may have missed this, but how did you get the red line to appear?
So do you have the link?
Yeah, I'm on it right now.
Okay. So the red line should already be there. If it's not, click the little circle next to the equation y equals mx plus b and make sure that that's toggled on. You should see a little red ball with a curly stripe through it.
Yes, I see it now.
Okay, good deal.
Okay, thank you.
You're welcome. So does anyone want to throw out there, some values for M and B that gave you a pretty good fit?
For M, I got 31.5, and for B, I got 1.
Okay. That looks really good. That looks really good. Yeah, no argument with that. Another possibility would be 32 and 0 for those things respectively. Again, both of those look like really good fits. The good news is we don't have to do this kind of stuff by hand. We have software that's going to take care of this kind of stuff for us. But in this case in particular, one thing that I want you to notice is that the slope is positive. So, qualitatively, you should be able to recognize a positive slope. Positive slope. Let's just draw ourselves a quick little sketch right here. Positive slope, that means when you move from left to right, your graph is slanted upwards. So something like that. You could also have a negative slope. And if you don't already have in your mind a picture of what a negative slope is like, go back to your equation and move the slider for m to something negative. In fact, take it all the way to left. I think it should go to like -20 and get a good feel for what it looks like to have a negative slope. So for a negative slope, you should see something that as you move from left to right, the line is pitched downwards. That is, the farther to the right you move, the farther down the y-axis you're going to move. So that's something else that can happen when you graph a line, is you can have a negative slope to your lines. There is kind of an in-between case. What's that in-between case? Can anyone suggest something that would be somewhat in between there?
Horizontal or vertical slopes?
Okay, yeah, horizontal. So a horizontal slope would be associated with 0 for a slope. And if you want, you can go back to our little link here and put in a 0 there. And take a look at the line that you get. It's just a horizontal line. So that's, again, another possibility that you can get when you're looking at the graphs of, well, when you're looking at data and the equations that try and summarize that data. So horizontal slope would look something like this. Now, horizontal slope is kind of a statistical bummer. It's like, all right, this really doesn't do us much good. Because if we look back to our data set, then let's put in the numbers that we're given, 31.5 and 1. That's a pretty good summary of the data. If I want to know what the value of x is, or if I know the value of x and I want to predict the value of y, I can do that. If, for instance, x is 2, then that's going to give me y is 64, at least according to this line. And that looks like a pretty good fit. So, and I can do likewise. If x is 4, then y is going to be 127, again, according to this line. So it's nice. You get a good fit to your data. Is it perfect? No. Because, for instance, at x = 4, the true value is 127.5. Okay. Now, what's wrong with a horizontal line? Well, a horizontal line is basically saying, you know what? No matter what value of x you give me, the value of y that I'm going to give you is still going to be the same. It's just going to be flat. So going back to making the 0, and we'll push this up to 20. If I tell you x is 2, you say, yeah, y is 20. X is 4, y is still 20. So it doesn't matter what value of x is, y is always the same. So basically your data is kind of uninteresting if you have something like that, because the value of x tells you really nothing about the value of y. You're just always going to say the same value. Now there is one other thing that can happen with our data that's a little bit beyond our course, but still can happen. Keep in mind we're looking for a linear relationship. And by that I mean something that can be summarized by a line so that you have data that are scattered around, like this or like this. Here, data is probably going to be kind of wildly scattered around a line, and when you try and fit a line to it, it's going to be pretty much flat. So that's kind of a bummer if that happens. But you could also have data that look like this. Now, as far as we're concerned, we can't actually work with this because it's beyond this course. We're just going to be looking for linear relationships. And although there's a relationship here, it's a non-linear relationship. It's not a line, in other words. So yes, there is something interesting going on here, but we're not going to address it in this course. You'll have to take some more advanced statistics to work with this kind of stuff. It's not hard. It's just, you know, there's only so much we can do. Now, you're not going to get much homework in this section from me because a lot of this stuff is going to be repeated in section 10.1 and 10.2. But I'll give you a little bit of a heads up. If you had a perfect linear relationship, that is, if all the data were on this line right there, then that would represent a correlation of R equals 1. On the other side of things, if you had all the data right on that line, none of the data off the line, that would be R equals -1. And then you get stuff in between. If you account for the data that's on the line and off the line, then maybe it's about 0.9, or maybe here it's about -0.9. But the farther away from a perfect line you get, the farther away from 1 or -1 you're going to get. And down here, that's just awful. R equals 0. That's your linear correlation. R is your linear correlation. Like I said, we're not going to really quiz you on that, but it doesn't hurt to plant the seed for this now, because we are going to work with this kind of stuff later. For now, I'd like you to be able to graph things and, you know, try and draw some meaningful information out of those. So I think page 75 is where we want to turn in our book. Let me see if I can't pull it up from our book here. Page 75. And we're going to plot some of our own data. So heights of fathers and sons. Okay, this is the table list in inches, heights of fathers and heights of their first sons from Sir Francis Galton. He's certainly a big name in the early history of statistics. But here's the data, and if you give me a second, I think we've got that in our Google Sheet someplace. If not, then I'll put it there for you. Done. No. Let's see. Let me try my Statdisk. See if I've got it there. No, I don't have it there either. I thought I had it someplace. All right, so bad news. We might have to do some typing here. Okay, so we are going to have to do some typing. Bummer. Let's do it in Statdisk. And what I'll do is I'll read off the numbers for you. So if you just want to concentrate on typing, that's fine. So going down the first column would be a 73, 75.5, 75, 75 again, and then 75 a third time, 74 twice. So after 74 twice, there's 73 twice. And then the last one is a whopper 78.5, definitely getting recruited to play basketball someplace. All right. How about over here? Height of first son. So in our second column, 74, 73.5, 71, 70.5, and after 70.5 is 72, 76.5, 74, 71, 72, and 73.2. Now, to my way of thinking, there's one of these observations in this data set is kind of odd. And if this was more of a serious endeavor, I'd probably look into it. But let me see about you guys. Is there anything here in this data that you kind of find odd or catches your attention just a little bit? It's nothing glaring, but it's curious.
The bottom
last-
numbers.
Which one and why?
For me, the 73.2 is off because it's not the, it doesn't end in a 0 or a 0.5.
Exactly. That's what caught my attention too. And I'm not sure if the other person was saying the same thing or not, but thank you both for jumping in here. Yeah, the last one is like kind of odd. So it's all of a sudden you're like, you got a 0.2 there. So that means all this time you had people that were exactly at the half mark or the even mark until the last one. It just feels weird. So in any case, it's not going to hurt us in this particular example. But like I said, if this was a more serious endeavor, I'd want to know a little bit more about that piece of data or the data set in general. All right, do we have the entire data set plugged in there? Is everyone with us on this? So you're on Statdisk online. Got the data in. Go to the data tab. Oh, there's a question? Somebody still working on that data? We're good there with the data? Okay, so all is quiet on the Western Front. Go underneath the data tab and then go to ScatterPlot and we'll click that. That should open up a new menu-driven program to help us create our scatter plot. Should look like this. Now the first thing you have to do is you have to tell it, where's your data? Okay, X values in column 1, Y values in column 2. Now you can do yourself a favor and actually label these things, plot options. So height of father versus son, for instance. On the x-axis was the height of the father, and on the y-axis is the height of the son. It's not a bad idea to put these things in there. That way you know them and you can make a better interpretation of the data you get. Now, in my naive way of thinking, I would hope and think that fathers and sons are pretty close to each other. So my guess at this, at least when I first looked at this data, I thought that there's going to be a positive correlation, but let's take a look at the plot of the data. In particular, the program seems to suggest this line. If that line represents the correlation of our data, what kind of a correlation is there between the height of a father and the height of the son?
Negative.
Yeah, slightly negative, or it's really kind of close to 0, meaning there's no correlation, right? Means knowing the height of the father tells you nothing about the height of the son, which is a little odd because usually those two things go together pretty well. So kind of surprising here, but that might just be a function of the fact that we've got a pretty small data set. Don't know. I would think that if we had more data, you'd see a strong positive linear relationship there. But right now, it looks like there's more or less 0 correlation, right? It's pretty random. I mean, in particular, there's a little bit of an outlier. You see the outlier? Which one of these looks like it just really doesn't belong? How about this guy?
78.
Yeah. Dad was 74 inches. The son was 78.5 inches. Wow. How tall is the mailman, right? You know, that's a big jump. So might be kind of curious about that. But really the point here was to get you practiced in the art of just putting in some data and getting a scatter plot. So what we'll do next is we'll try and do a little bit more work with the scatter plot once we get it. But are we okay with this one? All right.
Yep.
Let me see if question.
No.
I
Okay.
was just saying we're okay with it.
Oh, thank you. I appreciate that. It does help out because usually if we're in class, I could look at you guys and know that, yeah, they get it, or at least, you know, they somewhat get it. If I get this look of abject terror, then I know that I got to spend a little bit more time on the data. Now, speaking of data, I'm going to put some data in the chat here. And this is kind of a cool data set that I picked up along with Mike Volbach. He teaches history and geography for us here at OCC. It comes from the National Oceanic and Atmospheric Administration. And it's average temperatures in all 83 counties of Michigan going back to the 1890s. So, wow. Now let's just pick a county here. Let's see. Let's pick something up north because it's always fun to go up north. Charlevoix. There you go. So pretty near Traverse City. I'm going to pick out these for you. Now the good news is that you don't have to type any values in here. I'll put these in the chat. There. And just grab them out of the chat. And we're going to paste those right into Statdisk. So the original data set that I got a few years ago was comprised of average monthly temperatures for every month in every county, all 83 counties in Michigan, since, like I said, the 1890s. And I condensed that down. I thought every month was pretty tough to deal with. So I condensed it down to every decade. And that's what we have here. So let's put that into Statdisk. Go back to Statdisk Online. So you click that icon in the upper left-hand corner. And I'm going to paste that into columns 3 and 4. So if I put my cursor there, hit Command V or Control V, depending on what you've got, you should get something like this for your data. And let's do another scatter plot of the data. So in column 3, you've got the decade starting in 1890. So that's a 0. 1 is the next decade, the 1900s, etc. Where did I find my scatter plot command? Does anyone remember?
Data.
Under the data.
Yeah.
Under data. Good. Scatter plot. Select. This time I'm going to do columns 3 and 4. And we can title this decade versus temperature. On the x-axis, your independent variable is going to be the decade. And on the y-axis is the temperature. When you get those set, just hit the graph key. And bam, there you go. So you should get a graph like this. Does there look like a positive linear relationship, a positive correlation here between decade and temperature?
Yes.
Yeah.
Yeah, I think so. So there's a correlation between the decade and the temperature. Now remember, this is just a number of the decade, and I could have numbered the things anything, but we started with 0. That's okay. Think about this. There is a correlation between decade number and temperature number. But does that relationship go further? Is there a causal relationship? Does the number of the decade cause the temperature to go up?
No.
So I got one vote for no. What do you think? Does one cause the
No.
other? Does decade cause it? No.
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 A lot of factors that influence the weather, but you know, the number of a decade, the simple passage of time is not one of them. Not when you're talking about 10-year averages. No. So you're right. It's not a causal relationship. Now, this doesn't really say anything about global warming one way or another. This is just looking at one particular county in Michigan and seeing what's happened over the course of, 100 and some years, 120 some years. So nice.
So this is just kind of like where they would try to trick us because it doesn't necessarily explain why it's going up, right? But it is going up.
It is going up, yeah. And that's where you start looking at other variables that might contribute to that. So
Because at first glance I would say, okay, it's going up, but because
it is going up, yeah. But it's not the tricky part is that here, the two variables that we have are just correlated. It's not a causal relationship. It's like going back to how much TV you watch and how much you weigh. There's a correlation, but watching TV doesn't cause you to gain weight.
right.
No, it's related to that, but it's not a causal relationship. So
Okay.
yeah, no, that's, you said it's something that's tricky. I'm not trying to trick you in any of this stuff. I just want you to understand what's going on here.
Right.
Because that is something I will quiz you on. Can you decipher between correlation and causation? That's certainly something that I would have as a goal for you in this course. So great question. Thank you.
Thank you.
All right. That looks pretty good. How you guys doing with these scatter plots and things like that? Doing okay?
Doing
Yeah,
good.
I just have one question
Good.
now.
Yeah,
So
please.
if it's a zero correlation if it's a zero with a zero slope, would it be no correlation then?
Well, it's a great question. There are different types of relationships. This would actually have a correlation coefficient of 0 because this expresses the degree of a linear relationship. And even though there's a relationship here, it's not linear. So you'd get an R of 0 here. But I'm not sure I'd feel comfortable just leaving it at, oh, there's no relationship between X and Y. I mean, to me, it looks like there's a definite relationship. There's a, not to get too fancy here, but it'd be a quadratic relationship. It looks like a parabola, right? So, yeah, we probably sometimes want to go beyond just linear relationships. Unfortunately, in this course, we're going to be kind of stuck to just working with linear relationships. So, yeah, there'd be an R of 0 here, but I don't think I'd like in this particular example to say that there's no relationship here. So I'm trying to tread a fine line. Is that answer making sense for you?
No, that makes really good sense. So as long as there's an X and a Y, there's a correlation.
There's a possibility of a correlation. I mean,
Okay.
here's an X and a Y. And if I had this kind of data, there'd be no correlation, no linear correlation. If there's an X and a Y here, there is a relationship. It's just not a linear relationship. So the correlation would be 0, but there's still a relationship between X and Y.
Oh,
So
so
that's-
it depends on how you look at it, pretty much.
Yeah, a little bit. So if you're talking about, is there a relationship? Yeah, there's a relationship. Is it linear? No. So there you go. Anything else? Good question there. Thanks, Halal. Anything else there? All right. Hang on a second. So anything else on this section? All right then.